Good morning. Today we are going to see improper integrals of rational functions. Using method of contour integration, how to evaluate this improper integral of rational functions we are going to see. So two types we are going to see under that. One is integral of the form minus infinity to infinity function of x dx, and this function of x is of the form p of x by q of x. Both are polynomials in x such that the degree of q of x, the denominator, is at least 2 more than the degree of p of x. That is the condition upon this. And q of x does not vanish. Denominator should not be equal to 0. So with this condition only the convergence will hold. So therefore with that condition we'll evaluate and get the value for this integration, that is type 1. Type 2 is similar to this. See, we are going to evaluate equation of there is integration of this type, which is integration minus infinity to infinity f of x dx. This f of x is the rational function, and type 1 it is of this type p of x by q of x, and there is a condition for that. And type 2 function of x only, but it is of the form p of x by q of x into sine mx, sine mx in the numerator. Otherwise, p of x into cos mx by q of x. So it is sine or cos along with that. So we'll be using exponential function in common to represent this sine and cos. Imaginary means it is sine, real means it is cos. Okay, so we are going to find how to use method of contour integration to find the value of the integration of these two types. So first type, we are going to use Cauchy lemma here to get the value for that integration. So Cauchy lemma states that function f of z, remember the function f of z here, is continuous function such that mod z f of z tends to 0 uniformly as mod z tends to infinity on the upper semicircle CR. That upper semicircle is represented as C suffix R, which is mod z equal to R. Mod z equal to R means it is a circle center at the origin, radius R, above the real axis. Above the real axis, this is the real axis, this is imaginary axis, above the real axis. That is how the contour is defined here. Then integration over this upper semicircle f of z dz tends to 0 as R tends to infinity. This is a statement of Cauchy lemma which will be applying for evaluation. So first, the given problem is of this type as a function of x, but while starting with the problem, we'll consider that as function of z. The contour I'm taking here is integration over c. That contour consists of real axis from minus r to r and a semicircle cr above the real line. So I can split and rewrite this integration over the contour c, one in terms of a real axis, that is real line, another is upper semicircle. So I can rewrite this integration over c f of z dz. Together I'm writing this as f of z, and while writing with in the real line from minus r to r, I'm rewriting this as function of x because I'm writing on the real line. So it should be a function of x. Then next I'm taking the semicircle. There I have written integration over the semicircle, the same f of z dz here. So Cauchy lemma states that the integration over the semicircle f of z dz tends to 0 as r tends to infinity. Therefore, this integration will go to 0. Then remaining that r will take the value infinity. So I'll get minus infinity to infinity f of x dx. So that is what the problem which you have to evaluate. Then the left hand side of that is integration over c f of z dz. If you rewrite this in the left hand side and this integration in the right hand side, will look like this. And the value of this integration, we can apply Cauchy residue theorem to get it. So as soon as you see this integration over c f of z dz, you can remember that you should apply Cauchy residue theorem. This is the procedure to evaluate the integration, improper integrals of rational function, which is of type 1 of this form. So now consider this first example. Use method of contour integration to evaluate this integration. Here limits are not given to 0 to infinity. It is given as 0 to infinity. It is not from minus infinity to infinity. At last we will get this limit. Now consider the integrand, which is 1 by 1 plus x square the whole square dx. So now first I have to start with, how to start with this integration over c p of z by q of z dz. So wherever x is there, I have to take that x as z. So consider the contour C. The contour C is a closed curve consists of upper semicircle and part of real axis from minus r to r. So this is the contour with which we are going to evaluate the integration of this type. So now I'm splitting and rewriting this integration over this contour as one with the real axis, another with the semicircle, upper semicircle. Then using lemma, Cauchy lemma, it says that integration over C f of z is it tends to 0 as mod z equal to r, which tends to infinity. So therefore the above statement, this term will go to 0, and in this term instead of r I should substitute infinity, so that it will reduce like this. Now bring this and write it on the left hand side and write this in the right hand side, and the value of this integration is 2 pi a into sum of the residue by Cauchy residue theorem. Now my aim is to find the residues. So how to find the residues and all is already known to you. Similar procedure we have to use to find that. So only thing is you have to learn this, what contour you are using, and applying Cauchy lemma, how it reduces. That's all. Then as usual you have to consider that f of z and find singularities, etc. How to take this f of z means, see the integrand of the given problem. It is 1 by 1 plus x square the whole square. Instead of x, substitute z. That's all. You will get what is f of z. So it is 1 by 1 plus z square the whole square. Then equate the denominator to 0. You will get the singular points. You will get z square plus 1 equal to 0 means z equal to plus or minus I. Square root of minus 1 is I. You will get plus or minus square root of minus 1, which is plus or minus I. But whole square is there. It is repeated 2 times. So it is a double pole, not simple pole. So you have to change this. This is not simple pole. Then after finding the singular point, you have to check which point lies inside. So the contour is upper semicircle. So obviously these are the point plus I and minus I. Imaginary axis, only plus I will lie inside, minus I will be outside of this contour. So only positive side we are taking as the contour. So therefore z equal to plus I lies inside. Other points will lie outside. So it is enough if you find residue for that point which lie inside. So which is a double pole, remember. The double pole means it is limit z tends to I, d by dz of z minus I whole square. Here I have written here properly, it is whole square. Denominator 1 plus z square with root I have rewritten like this, and this is okay. Then if you substitute, if you cancel, differentiate with respect to z, you will get this term. Then take z as I, simplify, you will get the residue. Then substitute this residue where in this equation. If you substitute that residue here, multiply by 2 pi I, you will get the value for the integration, but the limits are from minus infinity to infinity. Okay, now substitute the function f of x, whatever is given in that problem. Then I have to rewrite this from minus infinity to infinity as 0 to infinity. How I can write that means, if the function is a even function, I can write negative to positive limit as 2 times of 0 to positive. So minus infinity to infinity, I can rewrite it as 2 times of 0 to infinity. So 1 by 1 plus x square whole square dx, and we got the value as pi by 2. Bring this 2 to the other side so that you will get the value for the required integral. Similarly, you try the second example. I have given what are the singular points you should get and the residues for the corresponding singular point. See here altogether you will get 4 singular points, 2 positive, 2 negative. So only upper semicircle is the contour. So only the positive values will lie inside the contour. So it is enough if you find what is the residue for those 2 points. Negative points you can leave it. So now you have to consider the residue, sum of the residue multiply by 2 pi I. You will get the value for the integration, but here it is from minus infinity to infinity. So we don't require any conversion here, directly we can get this answer. Similarly, you try the third and fourth problem, check whether you are getting this answer. Then next we are going to see the next type 2, integrals of the form limits are from minus infinity to infinity. That function of x is given like this in this format, where p of x sin mx by q of x is one type. Another form is p of x cos mx by q of x, and the condition here is m is positive, degree of q of x is greater than the degree of p of x. Q of x denominator should be, degree of the denominator should be greater than p of x. It is not like 2 more and all here, just the degree of the denominator should be greater, and it should not vanish, it should not be 0. Okay, so this is the condition for this integration. Now we are going to see the next lemma called as Jordan's lemma, which we will be applying to get the value for that integration. Jordan's lemma states that if f of z is a continuous function such that mod f of z tends to 0 uniformly as mod z tends to 0 on CR, where the C suffix R is the upper semicircle, and integration over CR e per I ms z f of z dz tends to 0 as r tends to infinity. This CR is a semicircle mod z equal to r, as I explained to you in the Cauchy lemma, similar to that. But here, along with the exponential function f of z, you're having exponential function. So there also in the problem also, you're going to convert and rewrite sine and cos as exponential. So this Jordan's lemma will be applicable for that type. So that this integration over c e per I m z f of z tends to 0 as r tends to infinity. And the procedure to evaluate this problem is, as usual, consider the contour and split and rewrite it, one with the real line, real axis, another with the upper semicircle. Consider the function of x as function of z here. Then Jordan's lemma, integration over the semicircle will tend to 0. Therefore, the problem will reduce like this. So then using Cauchy residue theorem, we'll get the solution. Similar procedure. First, we have to convert and rewrite this problem. If it is sine, it is imaginary, cos it is real. Okay, so that will do it. Next, I'm going to start the problem by taking the contour integration over c, and here I'm rewriting wherever x is there as z, and the sign I'm rewriting it as e per I m z. Actually, I should write it as imaginary part that I'm writing at the end. So as of now, we take it as e per I m z square plus a square dz, where c is the closed curve, upper semicircle, and part of real axis from minus r to r. I didn't draw the diagram here. That is very important. You have to draw the diagram here, which I already shown in the type 1. And now I can rewrite the integration over the contour C, split and rewriting like this, one with the real axis. While writing with respect to minus r to r, remember to write it as function of x, because it is on the real axis. It should not be in terms of z. So wherever x is there, you should write it as z. Sorry, wherever z is there, you have to write it as x. Then this portion, it is e power I m z f of z dz. Okay, function of z dz. This here we are going to apply Jordan's lemma. So this tends to 0 as r tends to infinity. Automatically this r will take the value minus infinity to infinity, so which is equal to integration over c f of z dz. So applying Cauchy residue theorem, I'm going to get the value. So for that, I require residue for the interior poles. So consider that function f of z. So f of z is this entire function. This entire function z e per I m z by z square plus a square. Now equate the denominators is 0, you will get the singular points, then which are simple poles because they are not repeated, and only the plus ia term will lie inside the semicircle, upper semicircle. Minus ia will go below that, so it does not lie inside the contour. So it is enough if you find the residue for that point, positive point which lie inside the contour, which is a simple pole. So directly you can find that. Then you have to substitute this residue here, 2 pi a into sum of the residue. So I have written here it is 2 pi a into sum of the residue. This is the value for this integration. Now the problem is minus infinity to infinity f of x dx. F of x dx is x e per I m x by x square plus a square, and the value we got it as this. Now I have to rewrite this exponential term as cos and sine, and then I have to equate the imaginary part because I should get sine term because that is a given problem. So at last I'm doing this. If you want, you can do it initially also, rewriting it as imaginary part. So now I'm rewriting exponential as cos and sine, and then I'm equating imaginary part. So equating imaginary part, here I'll get x sine mx by x square plus a square. Right hand side it is pi e per minus m, which is the coefficient of I, that is the imaginary part. So now limits are from 0 minus infinity to infinity, and I should write it as 0 to infinity. So if the function is even function, I can write it 2 times 0 to infinity. How to check the function as even function? If I replace x as minus x, I should get back the function f of x, so that I can say the function is even function. If you replace x as minus x, this will become minus x. This is sine of minus sine m of minus x, which is sine of minus theta, which is minus sine theta. So it is minus of minus, it will become plus. So there won't be any change in the numerator. Denominator x square is there. So if I replace x as minus x also, I'll get the same x square. So therefore no change, I'll get back the function f of x. So I can call this function as even function. According to the property of definite integral, I can rewrite it as 2 times integration 0 to infinity x sin mx by x square plus a square dx. And bring this 2 to the other side and rewrite it, you will get the value of the given problem.